This talk is about quantifying the strength of evidence from a study. It's based on a few chapters in the book Theory of Drug Development, which was published in 2013. In the United States, Europe, and Japan, there is a formal governmental process that drug companies have to go through to obtain regulatory approval to sell their drugs in each of these markets. So we can think about the strength of evidence from a study, say a phase 3 trial, in terms of how the study influences the marketing approval decision by these governmental agencies and the resulting benefits and costs that society incurs. Okay, so in order to take a formal look at when society benefits from a drug approval decision, let's set some notation. Let's let the probability of a true positive be denoted by P of plus and T. Here plus represents a positive trial and T represents the drug works in truth. Let the probability of a false positive be denoted by P of plus and F. Let's let A represent the benefit to society if the drug is approved and is effective. Let's let B represent the loss to society if the drug is approved and it's not effective. So with this notation, we can write the net societal benefit as we have here at the bottom of the slide. It's the probability of a true positive times A minus the probability of a false positive times B. This quantity represents the expected benefit to society if such a drug is approved. We will construct a measure of evidence that captures how the results from a study affect this quantity. Now note that although we did introduce the concept of societal benefit and cost, which are represented by A and B, it's not intended that we estimate A and B for every new molecule. Rather, we introduced A and B here to see what are the key statistics generated from a clinical trial that influence decision making when it is based on net societal benefit. We can rewrite the expression for the net societal benefit as we have here. In this re-expression, the net benefit is the probability of a false positive times the ratio of the probability of a true positive to the probability of a false positive times A minus B. So we can see here from this re-expression that whether or not society benefits from an approval decision depends on whether or not the factor in brackets is positive, and in particular, whether or not the ratio of true positives to false positives is sufficiently great in comparison with A and B. Now we can further rewrite the net societal benefit as we have here. We have some new notation, so let's look at the notation first. Let P1 represent the probability that the drug is effective, P0 represent the probability that the drug is ineffective, and let's let beta represent the power of the trial and alpha the type 1 error. So we can see from this expression that in terms of the results of a positive study, whether or not society benefits depends on the ratio of power to type 1 error, not type 1 error alone. Now, it's interesting to note that the ratio of power to type 1 error is also key to determining the posterior probability that the drug is effective, given that the study is positive, which is the key quantity that a Bayesian would rely on for decision making. Here once again, the notation is P1 represents the probability that the drug is effective, P0 the probability that the drug is not effective, and alpha and beta represent respectively the type 1 error and the power. So with this notation, the first line of this series equation is just a statement of Bayes' rule for calculating the posterior probability that the drug is effective. And the second line of the equations is just a re-expression by dividing both the numerator and the denominator by alpha. Okay. Now you might be thinking and asking yourself, how is summarizing evidence provided by a study with a ratio of power to type 1 error any different than how a typical frequentist or even a Bayesian would evaluate the results of the study? Well, it is indeed true that the description of study results with the ratio of power to type 1 error is very similar to the Bayesian frequentist descriptions in the case of a study that's evaluated only once at the final analysis. However, the addition of interim analyses to a phase 3 study adds complexity to the determination of the level of evidence that a study provides, and differences among these three approaches start to become evident. And the use of adaptive designs can add even more complexity to the description of evidence. So now if we think about the properties of an interim analysis plan that would be desirable, one of the first properties you would think of is that the level of evidence in favor of a positive treatment effect should be the same at each stopping point. In terms of our description of evidence, that would translate into the ratio of true to false positives given where the study stops should be constant at each interim. Now it turns out that this is equivalent to the ratio of the change in power to the change in type 1 error from the previous analysis is constant in each analysis, which is further equivalent to the ratio of the cumulative power to cumulative type 1 error is constant at each analysis. Well, let's take a look at one of the most commonly used interim analysis boundaries, the O'Brien-Fleming boundary, and see how it performs in this regard. So here in this slide we have an O'Brien-Fleming boundary with 5 equally spaced analyses in total. There's 82 subjects per group evaluated in the trial, and it has type 1 error of 0.025 and power of 80%. Now recall we know that a constant ratio of true positives to false positives given where the study stopped is equivalent to a constant ratio of cumulative power to cumulative type 1 error, as well as a constant ratio of change in cumulative power to change in cumulative type 1 error at each analysis. Here in this O'Brien-Fleming boundary, we see that these ratios are not constant. At interim 1, we can't compute the ratio because the power and type 1 error are so close to 0. However, at interim 2, the ratio of power to type 1 error is 77, and the ratio declines with each successive interim analysis and is 32 at the final analysis. In terms of the power over type 1 error conditional on where the study stopped, we see that the ratio is less than 32 at the final analysis. This is done by delta beta over delta alpha in the table. So we could actually subset positive studies with this stopping boundary into those that were positive only at the final analysis and those that were positive at earlier analyses. And we could draw the conclusion those that were positive earlier had stronger evidence supporting their approval than those stopping at the final. What's more, we could say the level of evidence provided by a study that only stopped at the final analysis is less than the weight of evidence provided by a positive study with no interim analyses at all. Since the ratio of delta beta over delta alpha is 15.7, which is half of 0.80 over 0.025 equals 32. So this is the downside of a stopping boundary that does not provide a constant level of evidence in support of a positive treatment effect at each analysis of the study. Now, this interim analysis plan includes a Pocock futility boundary along with a rejection boundary that maintains a positive ratio of power to type 1 error at 32. So we have 7 analyses of the trial results, including the final analysis. So let's take a look at the boundary itself. which is described in terms of the critical value for the z statistic. The rejection boundary starts out at 2.73 at the first interim, drops to 2.28 at the second interim, and then starts to increase, and at the final analysis ends up at 2.59. This contrasts with the O'Brien and Fleming boundary, which is monotonically decreasing. Another interesting thing to note about this boundary is that it allows for type 1 error exceeding 0.025. The type 1 error, so we can see that the type 1 error at the final analysis is 0.0289. Exceeding a type 1 error of 0.025 is justified in this evidential framework, since we saw as we developed the ratio of power to type 1 error that the type 1 error had no influence on whether society benefits from a drug approval decision. Only the ratio of power to type 1 error influences whether it's a positive or negative benefit to society. A couple things about the total type 1 error in this example to note. First, exceeding 0.025 on the side of type 1 error can also be justified in a Bayesian framework. And secondly, we could have constructed the boundary here so that the type 1 error is 0.025 at the final analysis. So if that's a constraint that someone still wants to adhere to, you can still apply the ratio of power to type 1 error as a measure of evidence. Now we will undertake a formal comparison of the evaluation of a study's results using the ratio of true to false positives with the Bayesian approach to evaluating the results from a study. So first, we'll develop an expression for the ratio of true to false positives. So let's let f be a prior on the size of the treatment effect theta. And we can express the ratio of true to false positives, given that we have stopped at interim I, as we have here. It's the integral of the probability of a positive study that stops at interim I times the density of the treatment effect theta, and then this is all integrated over the set of theta corresponding to a positive treatment effect. And finally, this quantity is divided by the same integral, which is integrated over the set of all theta corresponding to no treatment effect at all. So now we'll develop an expression for the posterior probability that the drug is effective that lends itself to a nice comparison with the expression we just developed for the ratio of true to false positives. So first let's define the function h. H of z is equal to z over 1 minus c, and it has a nice property that it's a monotone increasing function. Now when we apply the function h to the posterior probability that the drug is effective given the observed data x, we get the ratio of the posterior probability that the drug is effective given x to the posterior probability that the drug is not effective given x. And this ratio of probabilities can be rewritten as we have here in the last line of equations on the slide. So what we have here then is that Bayesian decision making, which is based on the probability that the drug is effective given the data that's observed, is related through a monotone increasing function to the ratio of two integrals, the ratio that's highlighted in the slide here. This means decision making based on the ratio of these two integrals is equivalent to Bayesian decision making based on the posterior probability that the drug is effective. So now on this slide, we have the two expressions we just developed for the ratio of true to false positives and the Bayesian approach. We have them here side by side for easy comparison. And as we can see, the difference between evaluating a drug using true to false positives versus the Bayesian approach is simply that the probability that the drug is positive given that the stopping boundary is crossed is substituted for the density of the observed data in the Bayesian approach. That is, True to false positives incorporates the data and the stopping boundary, while the Bayesian incorporates only the data and ignores the stopping boundary that was set up for the study. Don Berry, who's a famous Bayesian, underscores this as a desirable feature of the Bayesian approach and indeed ridicules frequentists for having to pre-specify everything that may happen in a trial. So one may be asking themselves, does this have any difference? Does this difference have any practical impact for a practicing statistician? Well, to answer this question, let's take a look at the following example. So here is, we have a simple study with two analyses, one midway through and the other at the final analysis, when 131 subjects have been enrolled and observed for the primary endpoint. There's a rejection boundary and a futility boundary, both which would not be expected to be binding in practice, since the z has to exceed 6 for the efficacy boundary and -5 for the futility boundary. So a frequentist would not reject the null hypothesis based on a positive study with this design because the power is too low, 63%. A Bayesian who's calibrated to mimic a frequentist, that is, reject when the study has 80% power and type 1 error 0.25, wouldn't reject the null hypothesis as well. So we're assuming we observed data something like 1.6 at the interim and 1.98 at the final analysis. An evaluation of power to type 1 error would not support rejecting the null hypothesis as well, since the ratio of power to type 1 error is 25 at the final analysis. So here now we've changed the example a little bit. This design is the same as in the previous slide, with the exception that the futility boundary at the interim is changed from -5 to 1.51. This has the effect of reducing the type 1 error from 0.025 to 0.0143. This phenomenon is commonly called buying back alpha. And changing the futility boundary as we did here also has the effect of reducing the power from 0.63 to 0.46. Now, a frequentist still would not reject the null hypothesis because the power is too low. A Bayesian would not reject the null hypothesis because the futility boundary doesn't enter into their consideration. However, notice that the ratio of power to type 1 error has now increased from 25 to 32. So that an analysis of power to type 1 error would lead one now to say that the evidence is sufficiently strong to reject the null hypothesis. So in the book Theory of Drug Development, which this presentation is based on, so a story is told about a magician who sends 5 predictions for the horse races to a lady, all of which turn out to be correct. After receiving these predictions and seeing the results of the races, she's convinced that the magician can predict the horses and is ready to bet all of her money on the next race for which the magician makes a prediction. What the lady does not know is that the magician sent lots of predictions for those same races to many other women, and she is the only one for whom all the predictions were correct. From the woman's perspective, the magician could predict the races, but from the broad perspective that encompasses all that the magician did, he's no better than anyone else at picking horses at the racetrack. So in the example that we've been discussing here, when the Bayesian chooses to ignore the futility boundary, he's essentially adopting the perspective of the lady who received the tips from the magician. The Bayesian is not using a probability model that encompasses all we know about how the data was generated, and so the Bayesian can be misled by his or her analysis. The frequentist has problems as well. As we noted, the frequentist would not reject the null hypothesis because the power is too low. However, frequentists are comfortable rejecting the null hypothesis at interim analyses with data that does not provide enough power to reject the null, as long as there is a plan to collect enough data that would provide sufficient power. it just doesn't seem appropriate that a plan to collect more data can influence the level of evidence that is considered to have been obtained at an interim. So it's interesting to think now about evaluating evidence from a phase 2, phase 3 clinical trial program. A study designed with a single futility analysis preceding the final analysis of the trial can be thought of as a phase 2 trial that precedes a phase 3 trial. The analysis of the phase 2 trial results corresponds to the futility analysis, while the pool analysis of phase 2 and phase 3 combined corresponds to the final analysis of the study. The ability of the ratio of power to type 1 error to capture the impact of the futility boundary allows it to quantify the strength of evidence provided by a phase 2, phase 3 clinical program. This is a feature of the ratio of true to false positive that is not shared by the Bayesian or frequentist approaches to evaluating evidence. Okay, so here we have a table that describes power over type 1 error for a phase 2-3 clinical program. And we can see here what the impact of the phase 2 futility boundary is on the power and the ratio of power to type 1 error for the phase 2-3 clinical program as a whole. As the threshold for passing to phase 3 becomes more strict, the ratio of power to type 1 error increases. So this threshold is presented in the second column of the table. It's labeled alpha futility. And the ratio of power to type 1 error that we're going to look at initially is in the last column of the table, and that's denoted by phase 2 and 3 combined. So for example, if we have a phase 2 threshold of alpha equals 0.9, the ratio of power to type 1 error for phase 2-3 combined in the last column is 33.4. While if the phase 2 threshold is alpha equals 0.10, then the ratio of power to type 1 error is 65.7, so almost a doubling of the ratio of power to type 1 error. What's also interesting to note here is that as the futility boundary becomes more strict, the sample size in phase 3 has to increase to attain the desired power, and after some point, the power has to decline regardless of what the sample size is. So for example, with a phase 2 threshold of alpha equals 0.90, the sample size required to achieve 80% power for the combined phase 2, phase 3 program is 335. And so the sample size is presented in the third column and is labeled in some phase 3, and the power is presented in the sixth column, and that's labeled power of combined phase 2 and 3. Okay. So like I said, to achieve 80% power with a phase 2 threshold of 0.90, the sample size required is 335. While with a phase 2 threshold of alpha equals 0.1, a sample size of 800 subjects in phase 3 only provides 39.4% power. And indeed, no sample size will provide 80% power. So from a frequentist perspective, a more strict phase 2 threshold does not increase the level of evidence, while from the net societal benefit perspective, or looking at power over type 1 error, a phase 2 threshold does increase the level of evidence. So another interesting point that's demonstrated in the table is that the ratio of power to type 1 error is greater when the phase 2 and phase 3 trials are considered separate with their own endpoints. That is, when the phase 2 trial is positive if the phase 2 threshold is exceeded, and the phase 3 trial is positive if it passes its own threshold. In other words, the evidence for the combined program is stronger when the notion of a confirmatory study is employed. We can see this in columns 9 and 10, which are labeled phase 2 and 3 separate, and phase 2 and 3 separate with an 80% powered phase 3. A threshold of 0.10 leads to a ratio of power to type 1 error of 155 and 126.6 respectively when phase 2 and phase 3 are evaluated separately, which compares with a ratio of power to type 1 error of 65.7 when the phase 2 and phase 3 portions are analyzed together in a combined analysis. So in conclusion, say that expectedness societal benefit model that we presented here provides additional theoretical support for hypothesis testing to support marketing approval decisions. The ratio of power to type 1 error as a measure of evidence allows us to specify interim analysis boundaries with the same level of evidence at each stopping point. And the ratio of power to type 1 error used as a measure of evidence allows us to quantify evidence from a phase 2-3 clinical trial program, while frequentist and Bayesian approaches to summarizing evidence have problems addressing this. So thank you very much. That's the end of the presentation.